Today's lesson is on plate tectonics. Some of this is a little bit of a reiteration from previous lessons, but it's important to refresh on this again before we start talking about plate tectonics. Earlier we talked about Earth's mechanical layers, the lithosphere, which is the rigid solid outer layer, and the asthenosphere, which is below it and is not completely a melted liquid, but is not completely solid either. It's described as being plastic-like and can flow. Okay? So the lithosphere, that outer brittle layer, is divided into sections called plates. And those plates float on top of the asthenosphere, that underlying plastic-like layer, like rafts, with the lighter parts riding up a little higher and making the continents, while the heavier parts ride a little bit lower and make up the ocean floors. And here we have a picture of the plates again, like we seen in the last lesson. This is something you could pause here and take a look at again if you would like to, and this would be might be really helpful and important to look at later when you're doing your assignment. Alright, so the lithosphere, like I said, is the Earth's crust and part of the upper mantle. It's approximately 100 kilometers thick. It's less dense than the asthenosphere, so it floats on top of the asthenosphere. Okay, just like everything else we've talked about when we talked about density. We said with air, with water, and with magma, the less dense material is going to rise to the top, while the more dense material is going to sink. Same thing with the entirety of the Earth. Okay, the lithosphere is the least dense part of Earth, so it is on the outside, and it's floating on top of the asthenosphere and the other more dense layers of the Earth. Alright, now the asthenosphere, again, is that semi-solid layer below the lithosphere. The rock in the asthenosphere is melted. It's not totally liquid, but again, it's still not totally solid. All right, we say that it's kind of plastic-like and can flow. The asthenosphere is more dense than the lithosphere. Therefore, like I was saying, it is below the lithosphere. Now, this picture here is in this presentation twice, and in the PowerPoint that you'll have twice. There's good reason for it. A lot of times with plate tectonics, we can really get bogged down with the literal descriptions of the plate boundaries and the types of movements. It's just real easy to get bogged down in the language and either get confused or just get things turned around or backwards. This picture helps clear it all up. In fact, this picture is one of the best reference materials you'll have when doing your assignment, because it tells so much of the story in very few words and one really great picture. Okay, you can see the movement of plates, right? You can see the different types of boundaries here, and you can see the different features the different boundaries cause. Okay, so keep that in mind as we go forward and when you're working on your assignment later, that this image right here is a very helpful piece of reference material for quickly reminding yourself of the details of each type of plate boundary and movement and associated geological features. Alright, so we have two types of plates. We have the continental plates, the ones that make up the continents. These are felsic and lighter, so they're more buoyant, they float better, so they ride higher on the asthenosphere. And then we have the oceanic plates. Those are the ones that make up the ocean floors. They're mafic, they're heavier, they don't float as well, they ride lower on the asthenosphere and make up our ocean basins. And I'm going to skip these questions for now. You can read these if you want to. They're going to be all answered as we go along. Alright, so let's talk about plate boundaries now. A plate boundary is any point where the two tectonic plates meet and interact. There are three main types of plate boundaries. divergent, convergent, and transform. Here's a breakdown of the specific plate boundary types. Okay, so we have our three main types. We have divergent, convergent, and transform. All right, divergent has two specific subtypes. Convergent and transform each have three subtypes. So with divergent, we have oceanic to oceanic. That means you have two oceanic plates coming together at a divergent boundary, or I shouldn't say coming together because divergent means moving apart, but they exist together there. Your two oceanic plates existing together with a divergent boundary between them. And the same thing could happen with two continental plates. You can have two continental plates with a divergent boundary between them. All right, convergent plate boundary types. This is where you have two plates moving towards each other. You can have two oceanic plates interacting that way, two continental plates interacting that way, or you can have an oceanic and a continental plate interacting that way. And then with transform boundaries, which are a boundary at which two plates are moving past each other, you could have two oceanic plates interacting that way, two continental plates interacting that way, or you could have that same interaction between an oceanic and a continental plate. And we're going to go through each of these in detail. All right, divergent boundaries. The name says it all. All right, diverge means to move apart or move away from each other. Okay, so a divergent boundary exists where two plates are moving away from each other. And we call that type of movement rifting. Okay, rifting of two oceanic plates we've seen before in the last lesson when we were going over seafloor spreading. When those two plates are being pushed away from each other by the magma that's rising at the mid-ocean ridge, the movement it causes of the plates moving away from each other we refer to as rifting. All right, the geologic features associated with divergent plate boundaries are mid-ocean ridges, which occur at oceanic to oceanic divergent boundaries, rift valleys, which exist at continental to continental divergent plate boundaries, and fissure volcanoes, which can occur at oceanic divergent boundaries or continental to continental divergent boundaries. All right, here's an image of the Mid-Atlantic Ridge. Okay, this is a big mid-ocean ridge that runs right through the Atlantic Ocean. This is one of those areas where we have seafloor spread, and you have magma rising up right along this ridge, and it's pushing this plate this way and this plate this way. As it does, it's creating new seafloor on both sides of this Mid-Atlantic Ridge here. Okay, so the Mid-Atlantic Ridge is a divergent oceanic plate boundary. All right, so that's why we have this mid-ocean ridge here. Remember, mid-ocean ridges are associated with oceanic divergent plate boundaries. This is a thermal image of the Mid-Atlantic Ridge. So you can see here, all right, the red indicates the hottest areas, where colors like blue here indicate the cooler areas. So you can see that right along this ridge here, that's where magma is rising up and pushing these plates away from each other. We have a few other kind of anomalies here, or what, like not right on the ridge but close to it. These here are underwater volcanoes. Okay, so these are spots where magma is also able to escape through the oceanic crust, right, and it builds up into these massive volcanoes on the ocean floor. Okay, oftentimes when we're studying oceanic to oceanic divergent plate boundaries, we end up talking about Iceland, because Iceland is the perfect place to study the Mid-Atlantic Ridge, because it is the one area of land that the Mid-Atlantic Ridge goes through. Okay, otherwise, in order to study it, you have to get images of the seafloor, and on Iceland you can study the same kind of divergence while being on land. So Iceland's always an important point of reference and an important place for plate tectonics research. Indeed, Iceland is actually a volcanic island. All right, this formed from magma escaping from the mid-Atlantic ridge, building up enough over time that it grew taller than the ocean surface, forming the island of Iceland. All right, over here we have, excuse me, here we have continental to continental divergence, okay? So we have a rift valley here. This is the Great Rift Valley is what this is known as over here in East Africa. This is where you have one continental plate going this way and the other one going this way. And again, they're being pushed apart by magma rising up through this large plate boundary here. Here's a picture of the Great Rift Valley in East Africa. And here we have a fissure volcano. So a fissure volcano is like a long crack in the earth through which magma escapes. We'll have more on that later when we get to volcanoes. All right, now let's talk about convergent boundaries. All right, these are plate boundaries that exist where two plates move towards each other and collide. And we have three types of convergent plate boundaries. All right, the first one is oceanic to continental convergent plate boundary. This is where we have an oceanic plate and a continental plate moving towards each other and colliding or crashing into each other. Subduction zones are a geologic feature that occur at this type of boundary. At a subduction zone, the more dense oceanic plate slides up under the less dense continental plate. Okay, so the more dense oceanic plate, it's heavier, it's riding lower on the asthenosphere. So when these two plates are pushed together, it moves under the lighter, more buoyant continental plate. So this occurrence creates also another geologic feature on the ocean floor called a trench. We're going to see pictures of a subduction zone and a trench in coming slides. All right, so also it's important to note volcanoes and earthquakes occur at subduction zones. So geologic features associated with oceanic continental convergence are subduction zones, an ocean trench, volcanoes, and earthquakes. Okay, here, this entire area here you would call a subduction zone because you have this more dense oceanic plate subducting under this less dense continental plate. Okay, the arrows here indicate the direction of movement. You have this plate moving this way, this one moving this way. All right, here you have that ocean trench. Okay, it's basically just this area where the edge of this continental plate is moving over the top of this oceanic plate, and it makes kind of like this V-shaped notch on the ocean floor. Here you can see that you have a line of volcanoes here, a volcanic arc. Right, this happens because as the oceanic plate is forced under the continental plate, you have friction all along here, and this melts parts of the continental crust. All right, and the melted parts rise up through the continental crust and create a line of volcanoes or a volcanic arc. Also, you get earthquakes from this friction between these two plates when these two plates move. Okay, most of the time the plates are more or less still, but what happens is the tension really builds up. You got this pressure building up between these two plates, and when the pressure becomes too much, that friction can't hold them in place, they slip and move, and that's what causes us to have earthquakes. All right, the Andes Mountains in South America. This is a good example of a mountain range created by subduction. Okay, you have the oceanic plate going under the South American plate, and it created the Andes Mountains. All right, second type of convergent boundary is oceanic to oceanic. You have two oceanic plates that are being forced together. All right, And the features associated with this are subduction zones again, trenches again, earthquakes again, and volcanoes again. Okay, so just like oceanic to continental, you get the same features with oceanic convergent boundary. Now, some things are different. All right, although both plates are oceanic, one is still going to be more dense and subduct under the less dense plate. So you have two very dense mafic oceanic plates, but one of those plates is going to be older and more dense, and it is going to go under the younger, less dense plate. Another type of geologic feature that's associated with oceanic to oceanic convergent boundary are island arcs. They're kind of like the volcanic arc we saw on land in the last type of convergent boundary, but because there's no land involved here, because we're talking two oceanic plates, you get these island arcs, which you can see here. Okay, so everything I talked about in the last video is the same except for just a couple details. All right, so again, we have this more dense plate going under this less dense plate. It creates a trench right along that boundary. Okay, again, you have friction here between the plates, and you have rising magma, but this time it doesn't create that, what we call that volcanic arc or that mountain arc, because there's no land. You have the seafloor here, so we get what's called an island arc, because eventually what happens is the magma that comes out cools and hardens to form these volcanoes underwater that eventually build up until they're tall enough that they rise out of the water and create these island arcs. The Aleutian Islands of Alaska is a good example of an island arc created by oceanic to oceanic convergence. You have a more dense oceanic plate going under a less dense one. The two plates are grinding. There's a lot of friction. You have melting rock off one of the plates, and it rises up through, creating an island arc. All right, the third type of convergent boundary is continental to continental. Okay, now this type of boundary, subduction may or may not occur. Oftentimes there is no subduction, but instead the plates collide and the front of both plates are pushed upward, creating mountain ranges. It's kind of like if you've ever seen a head-on collision with cars, the front of both cars is folded upward where the two cars collided. All right, this is more or less the same what happens when two continental plates collide. You get the front end of both plates pushed upward, creating a mountain range. Now in this example, we do have some subduction. You're going to have the more dense continental crust going under the less dense continental crust, but still we have this same compressional force pushing up this mountain range here. Now, when we were talking about oceanic to oceanic convergence or oceanic to continental convergence, those mountain ranges or those island arcs, those are volcanic. Okay, in this case, with two continents colliding, this mountain range is not volcanic. Here we have the Himalayan mountains. Right, this is an example of a mountain range formed by two continental plates colliding. Right, the Indian plate and the Eurasian plate collided. All right, and then the leading edges of both plates were forced upward by the compressional force of these two plates moving together, and this is how the Himalayan mountains formed. All right, now let's talk about transform fault boundaries. These are also referred to as strike-slip faults sometimes, and they can be part of larger divergent or convergent boundaries. Now, transform fault boundaries exist where two plates are sliding and grinding past each other. You don't have any kind of volcanic activity with this type of plate, but these are known for earthquakes. All right, here we have an example. The San Andreas Fault, which runs right along here and right through the state of California. All right, this is a classic example of a transform boundary. Okay, and you can see here these arrows indicate the direction of movements. You have the North American plate moving kind of downward and to the right. You have the Pacific plate moving upward and to the left a bit. And as these move, you get this grinding, and you get this friction going on between the two plates right here at this transform boundary, and this is what contributes to the earthquakes that are experienced out on the west coast. Here's a picture of the San Andreas Fault. You can see that you don't have any kind of volcanic activity or nothing. It's like a big crack in the earth, and you've got this side kind of going this way and this side going this way, and you get all this friction and grinding along here, which creates earthquakes. All right, let's talk now about the causes of plate tectonics. We mentioned this earlier when we were talking about the history of the development of plate tectonic theory, and now let's go a little more in depth. All right, the main cause of the movement of the plates are convection currents inside the earth. All right, hot magma, which is molten or melted rock inside the earth, moves toward the surface, cools, and then sinks again, and continues to do this in a cycle over and over and over again. We call this convection currents, of course. All right, and so these convection currents beneath the plates are what cause the plates to move. Okay, so here we have magma that's down near the core of the earth, which is the hottest part of the earth. All right, so this magma gets superheated and becomes less dense and rises. Okay, same with this magma here. All right, so it rises up here to that mid-ocean ridge, and it's putting pressure right here, forcing these plates apart. We call that ridge push. Also, that magma, not all of it can push up here, so the rest of it flows to the sides like this. As it flows to the sides, it creates friction here on these plates and pulls them along. All right, we call this slab pull. Okay, so you have ridge push here. All right, the magma's pushing the plates apart here. Then you have slab pull along here, and along here the magma is pulling the plates along as well. And here, all right, at these subduction zones, the oldest part of the plates are being forced back down into the asthenosphere, where they are melted and recycled into magma. Okay, all right, so I've already explained how the magma here gets heated and rises. Now here, as this magma is pulling on the plate, it actually cools off some. It becomes cooler than the rising magma. Now remember, all of this magma is super hot, okay? It's just that some of it is hotter than other parts of it, okay? So when I'm saying warmer or cooler or hotter and cooler, it's relative. It's all really hot, but some of it's hotter than other parts, okay? So the magma here cools off some, becomes more dense than the rising magma, so it sinks, okay, until it reaches, here close to the core again and gets heated again and becomes less dense again. All right, so it just keeps happening, this cycle of warming, rising, cooling, and sinking over and over again. And this is what drives these plates, kind of like a conveyor belt. It's like you have like a conveyor belt here driving these plates in the directions they're moving. All right, again, ridge push is associated with the oceanic divergent boundaries. This is what you're having happen right here. All right. Hot, less dense magma below Earth's crust rises toward the surface of that mid-ocean ridge and then flows sideways, pushing the seafloor outward in both directions, like I've been explaining. All right, gravity pull. This is something I didn't mention. This is associated with those convergent plate boundaries, okay? As the more dense plate subducts, in part because that's the way the magma is pushing it, it is also being pulled by gravity, okay? So this plate here, in addition to this magma pushing it this way and this magma pushing, also helping push it down, gravity is also pulling this towards the middle of the earth. Same deal here. All right, so the more dense, less buoyant plates ride lower on the asthenosphere due to their weight and the natural pull of gravity, like I've been explaining. Okay, this helps allow those less dense, more buoyant plates to ride over the more dense plate. Okay, so just to show you this again, this plate here is more dense than this plate. That's why this one is going down under while this one is staying on top. One more time, this picture here is going to be super helpful when you're answering your questions on your assignment. I'm not trying to discourage you from reading all this information again or listening to this video again. I'm just explaining that this picture should probably be your number one go-to, because the picture itself says everything that it took me all those words to say. Okay, so try to glean as much information as you can from this picture before you spend a lot of time reading through again. But please, if you find that reading through again is necessary, please don't hesitate to do it.